the terms of our sequence is R, I suppose I should say, 7 over 2, 13 over 6, 19 over 12, 25 over 20. And what's the last one going to be? Okay, here is a sequence. And hopefully you guys can read what I've written. And our job is to find a formula for the nth term. And as is typical for ones that are written like fractions, we're typically going to consider the numerator and denominator separately because it's going to make it easier. Usually they're kind of different. They're completely different from each other. Also, I will point out, someone could have tried to make this a lot harder by writing this term as 5/4, right? They could have reduced that fraction and made it look really kind of ugly by comparison. So usually that's not going to be the case, but if you see something where it looks like the pattern, like we can kind of see on the top, oh, the numerator is increasing by 6 each time. 7 plus 6 is 13, 13 plus 6 is 19, 19 plus 6 is 25, 25 plus 6 is 31. But if that had been 5/4, we might be like, oh, we probably need to change it so it looks more like the rest of the thing. So if you see something that looks kind of out of place, it might make sense to actually make it an unreduced fraction, right? Try and make it a fraction that looks like it fits in better. It's not the case here, but it is something sometimes people kind of try to do. So looking at the numerator, we definitely see we're increasing by 6 each time. So we're gonna need a 6n plus something, or maybe minus something, but probably plus something. Oh man, I've been totally forgetting about the symptom surveys. Like it's just been out of my mind. I'm sorry. So I should check all your symptom surveys. So if you could please show them to me, I would love to see them. I didn't teach a class last quarter, so I kind of forgot about all the symptom survey checking that we were doing way back when. So I will happily look at them. Thank you. Thank you. Cool. Yeah. Sure. Of course you did. Thank you. Thanks. You can show yours when it comes up. So great. So here, typically, although you don't have to, but if someone hasn't said anything, we usually start with n equal to 1. So if I'm saying my first term, a sub 1 is 7 over 2, well then for my numerator, I need a 6n plus 1. So that when I plug in n equals 1, I get 7. When I plug in n equals 2, I get 13. When I plug in n equals 3, I get 19, and so on and so on and so on. All right, great. What about the denominator? It's not super obvious. I see 2, 6, 12, 20, 30. We're definitely not increasing by the same thing each time, right? So like for the other one, it was plus 6, plus 6, plus 6, plus 6, plus 6 every time. Pretty straightforward. Here, for my 2, 6, 12, 20, 30, there's a couple ways we could do it. You might see it. It's definitely not something that's easy to see. So I see that we're increasing by 4, and then 6, and then 8, and then 10. So if I had to guess the next term, I think the next term of my sequence would be, let's see, the top would be 37, and the denominator would probably be 42 because we increased by 12. Thanks. That doesn't help us to figure out what the pattern is, right? I mean, it kind of helps us, but not like we don't know the formula for it. So what do? Well, I'm going to go back to that thing where I said, if you get to a place where the differences are all constant, it's kind of like you took the derivative that many times and got constants, meaning my second derivative is looking like a constant, which means I'm probably coming from something that's a second degree polynomial. So these numbers are probably coming somewhere from something like n squared. Now it's not exactly right. And this is really where you just kind of have to, you kind of have to play with it, right? There's no other like good way of being like, oh yeah, it's this. There's not like a great pattern recognition here other than you have to mess around with it. So, that's not quite right because like this is 1 squared plus 1 and 6 is 2 squared, but then I need a 2. Oh, wait, 12 is 3 squared plus 3. It looks like each term is n squared plus n. And it is. 20 is definitely 4 squared plus 4. 30 is 5 squared plus 5. It's definitely not the only way of writing this, but it's one way of writing it. So we could totally see that the denominator is n squared plus n. So our nth term is 6n plus 1 over n squared plus n. That's definitely a trickier one, in my opinion, where you've got something that's a higher power polynomial, but it's not exactly just n squared or n cubed or whatever. So these pattern recognition problems can be a little bit difficult. Something else I feel like I want to say about this one. I guess not. Questions about this one? Oh, that's weird. Okay. Let's see what else here. Let's look at another one. I'm sorry, where'd you go? Sorry, I've got papers all over the place here. Let's say we've got something like, yeah, say we've got something like this. 4, 3, 2, 3, 4. 3, 2, 3, 4. This one doesn't look terrible, except it kind of is. You're kind of going back and forth. 4, 3, 2, 3, 4, 3, 2, 3, 4, 3, 2, 3. Like, how would you write a formula for this one? Good question. Well, yeah, that's actually, I wasn't thinking, I was going to go a different direction, but that's probably even better. So yeah, you could go, I was going to probably use something kind of wonky where you do like a piecewise function kind of thing. That would work, but it's not elegant. Sine is much, or cosine is much better. In fact, I think I might actually put cosine here but sine would also work. You could make either one work, but I would do cosine. So I know that cosine goes 1, 0, negative 1, 0, 1. So I'm thinking of taking my cosine values, 1, 0, negative 1, 0, 1, etc., and adding 3. So I'm thinking, all right, I want cosine of what? What's actually going to get me what I want? Because I don't want cosine of n. That's not good. Cosine of 1, useless. Cosine of 2, not helpful. I actually want, well, what I really want is pi over 2 times n if I was starting at n equal to 0. But usually we start at n equal to 1. So we're actually going to do this. That's going to get us what we want, almost, right? If we plug in n equal to 1, we get cosine of 0, which is 1. If we plug in n equal, 2, we get cosine of pi over 2, which is 0. If we plug in n equal to 3, we get cosine of pi, which is negative 1. But we need to add 3. I bet sine would have also worked just fine. No, I think you go ahead. Right. So the reason I did pi over 2 is because I didn't say this very explicitly, is because when we graph cosine has these nice values of 1, 0, and negative 1 every pi over 2. So at 0, cosine of 0 is 1. At pi over 2, cosine of pi over 2 is 0. At pi, cosine of pi is negative 1. 3 pi over 2, cosine is 0. And at 2 pi, we're back to 1. So the reason we multiply by pi over 2 here is so that we get every multiple of pi over 2. Because we want to hit all the, for lack of a better word, corners. I know it's terrible to say corners of a circle, but it's what I've said always. We want to hit the 4 corners of the circle because those are the corners, the points that have nice values of cosine. So that's why we're multiplying with pi over 2 here, so that we get 0 and then pi over 2 times 1 and pi over 2 times 2 and pi over 2 times 3. So we're getting pi over 2 and 2 times pi over 2 and 3 times pi over 2, etc. It's a pretty common trick to get something that does this sort of thing, where you want to go above, kind of have like a middle and then above and a below. When you have 3 different values, you keep going back and forth between like that. A good way to get them is to use sine or cosine. In fact, sine probably would have actually been a slightly nicer choice here. We could have done sine of just pi over 2 times n plus 3. Because the sine function at 0 starts at 0, but at pi over 2 gives you a value of 1. So here, if you plug in n equal to 1, you're going to get sine of pi over 2 plus 3, which is 4. And if you plug in n equal to 2, you're going to get sine of pi plus 3, which is 3, and so on. You keep getting the values that you want. So, oh yeah. Let's look at some recursive sequences. So here's a great one. A sub n plus 1 is defined to be the square root of 12 plus a sub n. And we're given that the first term is the square root of 12, which, just so we all know, is approximately 3.46. All right, well, let's write out some of the terms here. So I should point out, here we're being given the sequence, right? We're not being asked to find the formula for it. It's given to us. But we are going to be asked to find, what does this converge to? So let's write out some terms. A sub 2 is 12 plus, sorry, the square root of 12 plus the first term. Okay, doesn't seem great yet. The next one's going to be the square root of 12 plus the previous term. Okay, that still doesn't really help me. The next one. So what I'm trying to say is none of these really help if I don't do more analysis. Meaning I actually might want to use a calculator and see what these things are getting closer to. Right? I don't know what that number is, but if I get a calculator, I can see it's approximately 3.93. And here, this one's approximately 3.99. So if I had to guess at this point, I would probably guess that it looks like a sub n is going towards the value of 4. It's a pretty reasonable guess. How do we show it? Excuse me. Well, here's what we're going to do. We're going to say, we're going to make the assumption that this thing probably converges. So we're going to say, okay, this is probably converging to some limit L. But if a sub n plus 1 is going towards L, so is a sub n, right? They both have the same limit because they're both the same sequence. This is just the next term in the sequence. So both of these things, a sub n plus 1 and a sub n, are going towards L. And then we're going to solve for this using our usual techniques of algebra, right? I'm going to square both sides. I'm going to bring everything to one side. And then hopefully I'm going to factor. This does factor as L minus 4 times L plus 3. So two possible answers are that either L equals 4 or L equals negative 3. And one of those is clearly not a good choice, right? We can see that this sequence, well, first of all, square roots can't give you negative values. So negative 3 definitely couldn't be the answer here. So this is not really a valid choice. It definitely looks like the limit is 4. right? We're getting closer and closer to 4. And if you plug in, well, no, sorry, I was thinking of a different thing. Sorry, thinking 17 series for a second there. 17 series does a similar thing, but like slightly different. So it's a pretty good bet that this sequence converges to 4. And there's a little bit more to say about that. Well, let's look at a slightly different example. Yeah, let's look at this. Sorry, I'm trying to keep track of all the things here. I'm doing a bad job of it. Yeah. One sec. I like having lots of papers, but then they get all over the place. So let's look at another example. Let's look at this limit. Limit as n goes to infinity of 4n over n plus 3. And I think all of you could tell me that the limit of this is what? Oh, question, sorry.
For the last example, why did we cross out L is equal to negative?
Well, so it's certainly true that if you're solving this equation, L equals -3 is a solution. But if we're thinking about what this sequence is getting closer and closer and closer to, our values start at 3.4-ish and are getting larger and larger and larger. So there's no way reasonably that this could get closer and closer to -3. So this actually brings up a kind of important theorem that this example will illustrate. So I think it's pretty safe to say that this limit is 4. Right? We can see that if the terms get bigger and bigger and bigger, we have infinity over infinity. You can use L'Hopital's rule, you can use one of the other rules you have, but there's kind of another way I want to talk about it. So let's make a couple observations. This rational expression is definitely less than 4. Let's check. Multiply both sides by n plus 3. Yep, that seems pretty clear. 4n is definitely less than 4n plus 12. Those cancel. 0 is less than 12. We're good to go. You could have picked a larger number. I picked 4 because it's the nicest one. The other thing I want to observe is that this sequence is non-increasing. It's not getting bigger. In fact, it's actually getting smaller. Let's see that. So then we're going to check that is we're going to check that the next term is smaller than the previous term. That is that a sub n plus 1 is smaller than or equal to a sub n. I read that the wrong. I always say it the wrong way. I apologize. Is that what I said that I said? It's not what I said that I said. Right. This is saying the next term. Why does my brain not want to say it the right way? Oh, that's because I'm saying the wrong, that's because I'm actually saying the wrong thing. Meaning it's actually not non-increasing. This is increasing. It's non-decreasing. Which means that I want the other thing to be true. So if I was checking for non-increasing, that's what I would want. To not increase, I would want the next term to be smaller than the previous term. But I actually want to show that this is not decreasing. Yeah, good job. Let's write this again. So this is non-decreasing. Well, they're not exactly the same. So non-decreasing means the terms could be increasing or they could be staying the same. Whereas increasing specifically means that they're getting larger each time. And increasing is a slightly stronger requirement that we don't actually need. So that's why we are specific and say non-decreasing. But yeah, for the most part, you should think this is essentially increasing here. But not exactly. So we're going to check that things are getting bigger, meaning the next term, a sub n plus 1, is bigger than or equal to the previous term, a sub n. If it was just increasing, we wouldn't have the equal part. So all right, a sub n plus 1 is going to be 4 times n plus 1 over n plus 1 plus 3. And we need that to be bigger than or equal to the previous nth term, a sub n being 4n over n plus 3. All right, is that actually true? It might be, but we can't just say it is right off the bat because both the numerator and the denominator got larger. And when both parts get bigger, the fraction could have gotten bigger, could have gotten smaller. We're going to check. Let's do some cross multiplication. This is 4n plus 4 times n plus 3 is supposed to be bigger than or equal to 4n times n plus 4. Multiply it out. We get 4n squared plus 12n plus 4n is plus 16n plus 12, bigger than or equal to 4n squared plus 16n. Yeah, that looks like it's going to work. The 4n squareds cancel, the 16n's cancel, and we get that coincidentally, and it is a coincidence, it's not by design or because of anything special, we get again that 12 is greater than or equal to 0, which is true. So great, we have a sequence 4n over n plus 3. It's bounded above, right? This sequence is definitely always less than 4, no matter what. And it's getting bigger, or at least it's not getting smaller. So we have that this sequence is bounded above and below, but specifically above we care about because it's getting larger. And is non-decreasing. That means something. It means, oh, sorry, it means you'd like to see what I'm writing. It means that it converges. If something has an upper bound, but is getting larger and larger and larger and larger and larger and larger and larger, there's no other choice. It can't get infinitely large because it's bounded above, but it can't like dip down and oscillate back and forth because it's non-decreasing, right? It's not getting smaller. So because of this, we can conclude that the a sub n equal to 4n over n plus 3 is indeed convergent. Now you might say, James, that feels like a lot of work for a limit we already know how to do. And it is. It's way more work than you need to do for this limit. But we're going to see pretty soon some examples where this idea comes back. That if a sequence is 1, bounded, and 2, monotonic, meaning it's either always non-increasing or always non-decreasing. Mono for singular, tonic for, actually, I don't know, for either increasing or decreasing. If those two things are true about a sequence, then the sequence must converge. It's kind of great. It's definitely going to come back real soon. So this also works if a sequence is decreasing or non-increasing. If it's getting smaller and smaller and smaller and smaller and smaller, and it's bounded below, then it can't get infinitely small or negatively infinitely large, and it can't oscillate back and forth because it's getting smaller and smaller and smaller. So that's why we say bounded, because when you say it's bounded, we mean above and below. So we should probably start talking about series because that's where we're going with things. Again, if you have questions or if you see me make a mistake, as I often I don't try to make mistakes, but sometimes mistakes happen. So if you see something like decreasing when it should be increasing or whatever, please tell me. I'm definitely not offended or proud or anything.
So when you say monotonic increasing and decreasing for these sequence, like the previous example we did, it was non-decreasing, which like you said, like it's not, it doesn't mean that it's increasing, but it could be like.
Right. So I mean, most of the time when we see it, like you could definitely say non-decreasing or non-increasing. It's easier to say increasing or decreasing because they're pretty much the same thing to us. Most sequences we see are not going to be non-decreasing, they're going to be increasing because most of the time things don't like stay the same value, but there are some exceptions. So that's why we tend to use this language instead. And really, to be even more kind of general, a sequence needs to eventually be monotonic, meaning it could do all kinds of crazy stuff for the first 20 terms. And then after that, as long as it's decreasing or increasing, depending on what you need, you're good to go. And that's actually kind of a very generally true statement about a lot of what we deal with. For series, for sequences, it kind of doesn't matter what happens in the first 1 billion terms or however many you want, as long as eventually it does the thing you need to do, which is kind of great because it means you can kind of ignore stuff until things that you want to happen. I'll say more about that as we go on, but it's a very kind of true thing. If you want to see if a series converges, doesn't matter if the first 20 terms do some wacky stuff, as long as afterwards it does what you need to do. All right, let's talk about series, also known as sums. And not that they have to be infinite, but most of the ones we're going to deal with this in this class are infinite sums. So an infinite sum or series is generally written as sum from n equals sometimes 1, sometimes 0. You can really start anywhere you want. 0 and 1 are the usual starting places of some sequence A sub n. And if we want, we can write it out like A1 plus A2 plus A3 plus A4, and so on and so on and so on and so on. And often the question we're going to ask about a series is, does it converge or does it diverge? Let's look at some examples. Let's look at this example. The sum from n equals 1 to infinity of 3n over n plus 1. So I'm going to start writing out terms. I'm going to get 3 over 2 plus 6 over 3 plus 9 over 4 plus 12 over 5. When I go way out, like to say the 100th term, I'm going to get 300 over 101. And then the next term is going to be 303 over 102, and so on. I'm adding up a lot of things. And I'm adding up things that are eventually getting pretty close to what? 300 over 101 is pretty close to 3. Oh, sorry, someone asked me a question. I didn't even see it. Sorry, if you're writing something on the chat and I don't see it, you're welcome to unmute yourself and ask, but I will eventually look up. Someone asked, what was the upper bound? I'm assuming for this question. Oh, no, for the previous question. So to back up, sorry. So for the previous question, one of the upper bounds, actually the least upper bound is 4. But you could have said an upper bound was 5 or 6 or 1,000, right? All those numbers are bigger than every term of this sequence. And then for this problem, the bounds, I mean, I would say your lower index is 1, your upper index is infinity. I think that's what you're asking about, but if you want to clarify, you're certainly welcome to. It's always the hard part with chatting, is like, they might be asking about the previous thing. I don't know. But feel free to, okay, all right. So this number close to 3. This number also close to 3. All these numbers out here, pretty close to 3. How many 3s am I adding up? A lot, like an infinite number of 3s. This is going to be infinity because I'm really adding up an infinite number of numbers all of which are close to 3. If I add up 3 an infinite number of times, I'm going to get infinity. So if I have something like this where the sequence gets really, really close to a number like 3, then the whole thing's going to diverge. This series diverges. I should also mention, though, it's because the sequence a sub n equal to 3n over n plus 1 converges to 3. Since all the terms of the sequence are getting closer and closer to some non-zero number, that means we're adding up an infinite number of a non-zero number, which is going to get you infinity. And it doesn't matter if they're converging to 3 or something really, really small. For example, for the same sort of reason, this series, n squared plus 2 over 100 n squared plus 5, this is also going to diverge. Why? Because our sequence is getting closer and closer to something that's not 0. The limit as n goes to infinity of the sequence is 1/100th, which, yeah, is pretty small. But if you add up 1/100th an infinite number of times, you're going to get infinity. So, yeah. These are actually both examples of what's called the nth term test, also known as the test for divergence. So the test for divergence, also called the nth term test, says exactly that. If the terms of your sequence don't converge to 0, then the series has to diverge. So if the limit of your sequence is not 0, then the infinite series must diverge. Equivalently, you can say, if the series converges, then the limit of the sequence had to have been 0. The same way, or different ways of saying the same thing. So if a series converges, the sequence had to have a limit that was 0. And if the limit isn't 0, then the series must diverge. Now, I should really, really emphasize here. This doesn't mean that if the sequence has a limit of 0, that the series is convergent. It's a really, really profound example of this. This series from n equals 1 to infinity of 1 over n, it's called the harmonic series. It's very famous. This series definitely diverges, which we'll prove later on. But I'm just going to tell you right now, this definitely diverges. When you add up 1 plus 1/2 plus 1/3 plus 1/4, and so on and so on and so on, it's going to be infinitely large. Even though the sequence definitely converges to 0. So when you're thinking about whether a series is convergent or divergent, it's important that the sequence has to have a limit of 0 to be able for the series to converge, but that's not enough. Right? The limit can be 0 of the sequence and the series can still diverge. That's why it's called the test for divergence. It can only tell you if a series diverges. It can never tell you that the series converges. The reason I'm emphasizing this a lot is because I see many, many people over the years say, oh, it converges by the test for divergence. And like, really? It says test for divergence. So I want to help you avoid making that mistake because it's a common one that's easy to do. Let's look at some more examples. Sorry, all over the place with the papers here. Also, for those of you that came in a little late, I forgot to bring the QR code for attendance. So you should at some point fill out the attendance form by going to the link on Canvas. That would probably be the easiest way. You don't have to do it right now, but at some point you should. So. I wrote lots of things down and then of course I just throw things everywhere. Let's look at a few more examples. What about this series from n equals 4 to infinity of cosine of 2 over n squared? It's a weird series, first of all, right? I mean, it's going to be cosine of 2 over 16 plus cosine of 2 over 25 plus cosine of 2, right? I mean, that looks awful in the first place. It might alternate signs. I don't know. It might oscillate back and forth between positive and negative things. But we don't really need to worry about that because we can think about what this limit is. Well, as n goes to infinity, 2 over n squared goes to 0. And that's going to be cosine of 0, which is not 0. That being not 0 automatically means, oh, this series has to diverge. No other choice. So that's the power of the nth term test, or the test for divergence, is that you should always be thinking when you're dealing with a series, could it converge? Could it diverge? Well, let me check the sequence. If the sequence doesn't go to 0, I'm done. My series has to diverge. Here are a couple more examples. This is one of my favorite ones because people kind of look at it like, what could I do here? People try using there's a lot of tests we're going to talk about that we haven't covered yet, obviously. One of the tests is called the nth root test, which would be very maybe applicable here, although it actually doesn't work, but you would think, oh, nth root test seems like a good idea here, but it doesn't work. I really want you all, when you're talking about seeing if a series converges or diverges, to kind of first think of, can I use the nth term test? Does that sequence have a limit that's 0 or not? Well, what's the limit as n goes to infinity of this sequence? Well, I know what it isn't. I know it's not 0. I've got something that's greater than 1 being raised to a power that's getting larger and larger and larger. For sure, it's not 0. Although it definitely is a limit we should know. It's E. So since this limit's not 0, great, this diverges. All right, but we might be a little more interested in some series that actually converge. So let's look at some other examples. Let's look at, this is a pretty classic example. Let's look at the sum from n equals 1 to infinity of 1/2 to the n. So first and foremost, let's ask ourselves, could it converge? Well, let's take the limit as n goes to infinity of the sequence, 1/2 to the n. as n gets larger and larger, we're going to have 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which is going to get smaller and smaller and smaller. This sequence has a limit that is 0. What does that tell us? It tells us nothing. But what it doesn't tell us is it doesn't say specifically that this series diverges. So all this means here really is we have to do more work. At this point, the series might converge, but it still might diverge. So when the limit of the sequence is 0, what I think of is, oh, we have a chance of the series converging. It still might not, but it might. Whereas it being not 0 is a definite, you're done, the series diverges. Okay, so this is probably where we start talking about the sequence of partial sums. So the first partial sum is just the first term, which is going to be 1/2 to the 1, which is not exciting. The second partial sum is going to be the first two terms added together, which is going to be 1/2 plus 1/4. I've made an assumption here that we often just make, is that my sequence a sub n is 1/2 to the n, right? We kind of just often say, if you've got a series, the series of the sequence is called a sub n. The third partial sum is 1/2 plus 1/4 plus 1/8. Now we could actually start simplifying these things, but I want to make a point. We don't actually need to see that it converges, because no matter what, each time I'm adding half the previous term. If I keep doing that, well, I can see that my sequence of partial sums has two qualities. One, it's bounded. Whatever my partial sum is, take the 10th term, the 20th term, the 1000th term, each term in my sequence of partial sums is certainly bigger than or equal to 1/2 for sure. And I'm not going to make the obvious, maybe I'm not going to make the exact choice here. I know for sure that each term is less than 2. 100%. Right? If I'm taking 1/2 and adding 1/4, I can't get above 2. If I keep adding essentially half the difference between this number and 1, there's no way I can even get above 1. I made a larger choice just to kind of point out that you don't have to choose the exact right number, right? I'm a quarter of the way from 1 here. Right? I added half of that. I'm an eighth of the way from 1. I added half of that. I'm a 16th of the way from 1, right? Each time I'm still not even getting to 1. In fact, we could write the pattern we start writing it out, it starts to become maybe really evident what the pattern for this nth partial sum is. But we don't need that, because if your sequence is bounded and certainly non-decreasing, or increasing would be a nicer thing to say here. This is what's great about sequences of partial sums, is if your original sequence has all positive terms. So my original sequence, a sub n equal to 1/2 to the n, all the terms definitely positive, without a doubt. So if your sequence that your series is being built from has all positive terms, well, then your sequence of partial sums has to get larger, right? Every time you add the next term on, you're adding something that's positive, meaning the next term has to be bigger than the previous one. So it's certainly true that S1 is less than S2, is less than S3, is less than S4, and so on, all the way to something like this. Each term is smaller than the next one. But those are the two things we need to say that the series, sorry, I really should say the sequence of partial sums converges. So this is enough to say, hey, this sequence of partial sums converges because it's bounded and it's non-decreasing. It's getting bigger and bigger and bigger, but it can't certainly be bigger than 2, so it has to get closer to some number. And the number it gets closer and closer to is 1, right? We could have said it's bounded above by 1, but I picked 2 just to change it up a little. So how do we actually see what it's converging to? Well, we have to find a formula for the sequence of partial sums. And sometimes you can just see it by inspection. Here we can see it looks like the nth partial sum. Well, the denominator looks like the nth power of 2, and the numerator looks like 1 less than that. Now, taking the limit of this might not be super fun, but it's much better if we write it as 1 minus 1 over 2 to the n. Then we can see that the limit as n goes to infinity of 1 minus 1 over 2 to the n is just 1. So this sequence of partial sums converges to 1, which means the series converges to 1. So we would write this. No, it converges. So let me, this is where the language gets to be a little bit terrible. The original sequence converges to 0. The sequence of partial sums converges to 1.
Oh, got it. Okay. So, yeah.
So let me say some things and then we'll come back. So here's what we're saying. In general, you might like to see. We have a series, an infinite series from n equal to 1 to infinity of a sub n. And a sub n is the sequence of often positive terms, although they don't have to always be just positive. A1, A2, A3, A4, et cetera, et cetera, et cetera. And then we make a new sequence from that sequence. Oh, sorry, people are asking things on the chat. Yeah, good question, good answer. They're asking why is the upper bound 2 and not 1? They're both upper bounds. 1 would be the least upper bound, but literally anything above that would also be an upper bound. So yeah, good answer. So then a new sequence that we're going to create of partial sums. So the first partial sum is the first term. The second partial sum is the sum of the first 2 terms. The third partial sum is the sum of the first 3 terms. Right? It's a partial sum because we're not adding up everything. We're just adding up part of it. And we just keep going. All the way down to some nth partial sum. So here's the idea. S sub, I should probably use a capital N there because that's more standard. Sorry. More standard, use a capital N here. So the nth partial sum is this. It's the sum from n equals 1 to capital N of a sub n. Well, great. Then I can do this. The limit as capital N goes to infinity of S sub n is going to be the infinite sum. So if this limit converges, then we say that this sum, this infinite series, converges to that limit. it's kind of linguistically more complicated than it needs to be. But that's what the language really is saying there, is that we don't just want to say you plug in a thing, you get a thing. We kind of want to make it more complicated than it needs to be, maybe. But we're going to take the limit of the partial sums, and if that limit converges, then we get to say that the series converges. And there's a number of examples of this. Let's look at another one, which I think is a good example. Let's look at, do we want to make, yeah, let's make it a little, we'll make it a little challenging. It's not too terrible, I promise. So let's look at the infinite sum, 1 over n squared plus 5n plus 6. And let's write out some terms. So let's say I'm going to get 1 over 1 plus 5 plus 6 is 12. 1 over 4, oh man, maybe I should factor this. Might be easier. This factors as n plus 2 times n plus 3. That's going to be 1 over 3 times 4 plus 1 over 4 times 5 plus 1 over 5 times 6. Okay. So here's my sequence of partial sums. The first partial sum is 1/12. The second partial sum is 1/12 plus 1/20. No, I don't want to make that a simpler fraction. You don't either, I promise. The third partial sum . The problem here is that I don't see a pattern. Maybe we would start to see a pattern if we got some common denominators. I don't think you actually do, really, because there's another way of dealing with this. So we're going to use a trick actually from 21B. We're going to do a partial fraction decomposition. Partial fractions coming back at you. So check this out. 1 over n plus 2 times n plus 3. We can rewrite that as a over n plus 2 plus b over n plus 3. And we can multiply both sides by the common denominator to get 1 equal to a times n plus 3 plus b times n plus 2. There's a number of ways for solving for a and b, but the easiest way is what I call picking convenient values of your variable. So we're going to pick n equal to -2 and get 1 equal to a times 1. Great. A equals 1. And we're going to pick n equal to -3. And we're going to get 1 equal to b times -1. So b equals -1. So what we're going to do now is we're going to rewrite this as the sum from n equals 1 to infinity of 1 over n plus 2 minus 1 over n plus 3. This is a common tactic, by the way. If you've got something where the denominator factors, often someone's looking for you to use partial fraction decomposition to get what's called a telescoping sum. So here's how someone would probably do this the short way. In fact, let's get a little more room here. So if I was trying to answer this question kind of as quickly as possible, I would probably write out the following. I'd say, okay, well, plug in n equals 1. I get 1/3 minus 1/4. Plug in n equals 2. I get 1/4 minus 1/5. Plug in n equals 3. I get 1/5 minus 1/6. And what's going to happen? What's going to cancel? -1/4 and +1/4. -1/5 and +1/5. -1/6 and the +1/6 right there. And so doing it this way, we can kind of see that the series is going to converge to 1/3. And while that's really probably perfectly fine, it's a little imprecise, meaning here's the work some people might want to see. So let's write out the sequence of partial sums. So here's my first partial sum. it's 1/3 minus 1/4. Here's my second partial sum. It's 1/3 minus 1/4 plus 1/4 minus 1/5, which is 1/3 minus 1/5. Let's do one more and then we'll go big. The third partial sum is 1/3 minus 1/4 plus 1/4 minus 1/5 plus 1/5 minus 1/6, which at the end of the day is going to turn out to be 1/3 minus what? Yeah. Sorry, sometimes my 3s look like 5s. So it looks like when you do this sort of telescoping sum, it's called telescoping sum because like all the middle things cancel out. You're going to get 1/3 minus kind of whatever the last thing is. So if we go down to the nth partial sum, we're going to get 1/3 minus 1/4 plus 1/4 minus 1/5 plus dot, 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 dot. I usually like to write the last two terms to make it a little bit more obvious. So when I plug in n minus 1, I get 1 over n minus 1 plus 2. So 1 over n plus 1 and 1 over n minus 1 plus 3. So 1 over n plus 2. And then when I plug in n, I get 1 over n plus 2 minus 1 over n plus 3. And now I can see that's going to cancel with that. That's going to cancel with that all the way till this is going to cancel with the thing that came before it. This is going to cancel with that. And so my nth partial sum formula is 1/3 minus 1 over n plus 3. And now we can say, well, what's the limit as n goes to infinity of this nth partial sum? Well, it's the limit as n goes to infinity of 1/3 minus 1 over n plus 3. And this part's definitely going to go to 0. So we get 1/3, which shows us that this series, the sum from n equals 1 to infinity of 1 over n squared plus 5n plus 6 converges to 1/3. Although the shorter way to write that would just be to say it's equal to 1/3. So when you say a series is equal, I should say, when you write that an infinite series is equal to a number, all the kind of language that's involved in that is really you're saying, I'm not actually saying it's equal to it. I'm saying the limit of the partial sums converges to it. But we don't really care that much. We really do. Like, so for the most part, if I was doing this, I'd be like, oh yeah, this series here, 1/3 to the n, for example, from n equals 1 to infinity, even though I know I should really say it converges to the value it converges to, I might just be lazy and write, oh, that's going to be 1/2. I know you, and we'll talk about why it's 1/2 in just a second, I promise you. But, right, instead of converges to 1/2, because they mean the same thing. So I would encourage you not to try, like, as I am, try not to get too caught up in all the words. It's okay to say the series is equal to a thing, even though it actually means we're really saying its limit of partial sums converges to that thing. All right, I've talked a lot. Is there any questions? Yeah.
Yeah, so I got confused on I got the one. Yeah, when you went from like the 1 over n plus 2, like n plus 3, and then like I know we learned that from like 21B, that whole thing. But like, why do we use that?
My best not great answer to that question is experience. I've seen problems like this before. I mean, I made up the problem because I definitely knew what I was supposed to be doing. But like, you will see problems like this where you have 1 over typically a quadratic that factors into like an n plus 2 and an n plus 3, or an n plus 3 times an n plus 4, or usually two things that are consecutive. Sometimes they can differ by more than 1, but they usually differ by 1. So when that happens, often the tactic we use is to rewrite it as a sequence of partial, as a partial fraction decomposition. Because we can see here, oh, when we start writing out terms, things are going to cancel. But yeah, it really, the not very exciting answer to that question is experience, practice, doing it a lot. Let's take a look at this other one here. So there's something that is true, I think. Let me double check the numbers here. Yep, that should be 1/2. So how do we know that, or how do we show that? Well, let's look at this example. So if we start writing out terms, we get 1/3 plus 1/9 plus 1/27 plus 1/81, so on and so on and so on. And we start writing partial sums, things start getting a little ugly. 1/3 plus 1/9 is 3/9 plus 1/9, which is 4/9. And then if we do it, so tip, instead of writing all 3 terms, the next partial sum is the previous partial sum plus the next term, right? I've been probably doing more work than I need to. We can save ourselves a little effort here and say, oh, that's going to be 4/9 plus 1/27, which is really 12/27 plus 1/27. And the fourth partial sum is going to be the previous partial sum plus the next term, which is going to be 39 plus 1/81. And at this point, you might start to see a pattern. You might start to see that the numerator times 2 plus 1 is equal to the denominator. You might not, right? It takes practice. But 1 times 2 plus 1 is 3. 4 times 2 plus 1 is 9. 13 times 2 plus, this is where I start to like, oh yeah, 13 times 2 plus 1 is 27. 40 times 2 plus 1 is 81. So we might be able to write a formula for the nth partial sum. We can probably reasonably guess that, let's see, the denominator is 3 to that number, right? 3 to the first is 3, 3 squared is 9, 3 cubed is 27. Yeah, seems good. And the numerator seems to be, oh, I have to go backwards. I said it was the numerator times 2 minus plus 1, so I have to undo that. So I have to do my denominator minus 1 divided by 2. So 3 to the n minus 1 divided by 2. There's my not very pretty looking formula, but it's probably right. It's definitely right. How do we get that in general though? Well, there is a way. There's actually a very specific formula for these geometric series, which we'll talk about. Yeah, we can talk about for the day. Sorry, the chat, I keep looking over here. I need to I should move the screen a little over this way maybe. Okay. Thank you people in the chat for answering questions for the people. It's always good. So if we look at this, let's rewrite it. It's going to be 1/2 times 3 to the n minus 1 over 3 to the n, or 1/2 times 1 minus 1 over 3 to the n. And we can see, oh yeah, the limit of that well, this part's definitely going to go to 0, so we're going to get 1/2. Do we need to do all this work every time we're trying to show what a series converges to? No. But it is important to be aware that when you're talking about a series being convergent, you're really talking about the limit of its partial sums being some value, right? You're finding the limit of the partial sums. We're going to develop techniques for various things to show that they're convergent without having to do all this work, but this is kind of the basis for saying a series is convergent. Let's see here. Let's take an example too. Yeah. Oh yeah, we should do that. That's a good example as well. That's a good one more example. Well, I would say one more example, like it's gonna be the last one. We got plenty of time for more than one more example, probably. So let's look at this series. So from n equals 1 to infinity of the natural log of n plus 1 over n. Oh yeah, go ahead. Oops, you made me like to see things though. Yeah, but go ahead.
So I know like I could have just gone lost, but so for like the partial sums, it's like for the series, like like with the it only converges like with the divergent rule, like it has to equal 0.
The limit of the sequence has to be 0. The original sequence. So that's a really good question. So if I go back here for just a second, you're right. And I was actually just about to say, I did myself a disservice, new disservice. We didn't check to see if the the nth term test applied here. So we should have started off by checking. What's the limit as n goes to infinity of the sequence? What is that limit? Definitely 0. So we're safe. This one could converge, but it could also diverge. It didn't, right? We definitely showed it converged, but it could have possibly diverged. And in fact, going back to the previous example as well, we should have checked here as well. This sequence, a sub n equal to 1 over n squared plus 5n plus 6. If we take the limit as n goes to infinity, what do we get? Okay, good. All right. So we're safe, right? But it has to be the case that if the series converged, I'm going to say that again, if the limit of the sequence of partial sums converged, then the original sequence had to have converged to 0. And I think some of you might be getting a little caught up by the fact that there are two different sequences going on here. There's the original sequence. In this problem, the original sequence was this. And then there's the sequence we're making up, the sequence of partial sums. So this sequence converged to 0. This sequence of partial sums converged to 1/3.
So we only use the partial sums in a series.
Right. It's always the sequence of partial, right? So when you say the word series, you should think sum. A series is a sum is a series. And so when we're doing the sequence of partial sums, it's the sequence of partial series. So we're just saying, oh, the first term of the series adds up to this. The first two terms add to this. The first 3 terms add to this. But yeah, they're totally different things. They're related to each other, but they're very different.
Yeah, and then so for not the example with like the 1/3 power of n, but the one before that, so we got converges to 1/3.
Yeah.
I thought like just for me, I thought like it with the rule for like the partial sums, like between 1/2 and 2 to partial sum.
Oh, sure. Yeah, I see what you're saying. Excellent. So yes, we didn't say anything about that, but you could have made the observation here that the first partial sum is what? 1/3 minus 1/4, I think is 1/12. So you could definitely have said, oh yeah, our sequence of partial sums is definitely always bigger than or equal to 1/12. I don't know if I know exactly what, but it's definitely for sure less than or equal to 2. Right? There's no way that that's
It changes for every
right. Yeah. It's not always going to be the same. I mean, you could have said, right, 2000. The hard part about this is it's not always super obvious that something is bounded on the side it needs to be bounded on, specifically above. Like it might not be really, really clear that this has an upper bound. It does, but it's not always easy to see what it is.
So for lower bound, like 1/12. Oh, right there.
Yeah. Usually it's just the first term. You're right, but we didn't use that theorem. We didn't use the fact that this sequence of partial sums is bounded and increasing. It is. It's definitely bounded. It's definitely increasing, right? Each term is bigger than the previous one. 1/3 minus 1/4 is definitely smaller than 1/3 minus 1/5, which is smaller than 1/3 minus 1/6, which is smaller than 1/3 minus 1/7. So we can see, oh yeah, it's bounded. It's increasing. It's convergent. A lot of the time we use that theorem and we kind of can't do anything else. So most of the time, if we can, we like to just find the formula for the sequence of partial sums because it's nice. You actually get to figure out what something converges to. But sometimes we can't do that. And so we kind of fall back on that theorem where we're like, well, we can see that it's bounded. We can see that it's increasing. So that's good enough to show that it's convergent. So let's look at this next example. And we should definitely start off by checking the test for divergence, aka the nth term test. So if I take the limit as n goes to infinity of my sequence, well, let's ignore the natural log for a second. As n goes to infinity, what happens to n plus 1 over n? Where does it go to? You can show me on your fingers, as long as you don't use that finger. Good, thank you. Yeah, right. You're like, what is he? Oh yeah, there's only one, right? So that limit of that is definitely 1. So what's the limit of that? Great. What does that mean? Right, exactly. That's the best answer I can think of. If the limit of the sequence is 0, it means the series could converge, but it could also diverge. It really means at this point, anything can happen at this point. The series could converge, but it could diverge. Okay. This is also actually an example of a telescoping sum. We're going to use a logarithm rule to rewrite this as the sum from n equals 1 to infinity of the natural log of n plus 1 minus the natural log of n. And here is where being precise is actually really important. If you just write out the first few terms and say like, oh, things cancel, it works out fine, things don't work out fine. Here's what I mean. So I'm going to write out the first few terms and just show you what I mean. So we have natural log of 2 minus natural log of 1 plus natural log of 3 minus natural log of 2 plus natural log of 4. Wow, my L sometimes. So if you did that and said, okay, things cancel, natural log of 2, negative natural log of 2, natural log of 3, negative natural log of 3, natural log of 4, negative natural log of 4. All the things cancel. That's a lie. All the things don't cancel. If we were not being very careful, we might say, well, this converges to 0 because natural log of 1 is 0. That's wrong. It's very wrong. And we start writing out terms, you can kind of see that's wrong because the first term is going to be natural log of 2 plus natural log of 3 halves plus so on and so on and so on. We definitely shouldn't get 0. All those things are positive. What's going on here? Well, what's going on is we need to be more careful. So let's write out our sequence of partial sums. The first partial sum, natural log of 2 minus natural log of 1. The second partial sum, natural log. So I'm gonna try and kind of cut to the chase here because we're short on time. If I add the first two things together, what do I get? Well, I still get the natural log of 3 minus the natural log of 1. In fact, I could really just do without that as well, right? The third partial sum is going to be this plus this plus this. The natural log of 2 is canceled. The natural log of 3 is canceled. I'm left with the natural log of 4 minus the natural log of 1. So if I had to venture a guess, I would guess that the nth partial sum is the natural log of what? Yeah, exactly. And that's where the problem is. Because if the nth partial sum is the natural log of n plus 1, and we take the limit as n goes to infinity of our nth partial sum, we're going to get the limit as n goes to infinity of the natural log of n plus 1, which is infinity.
Wait, hold on.
Sure.
S of 2, the
So I skipped. I was a little abbreviated in showing my work here. So S2 is the natural log of 2 minus the natural log of 1 plus the natural log of 3 minus the natural log of 2. And then those terms cancel.
Oh, I see. Okay.
And then S3 would be these first 3 terms, and we'd see this canceling and this canceling. Oh, sorry, this canceling and getting this minus that. Okay, so then this limit isn't 0. It's in what? 0. Whoa, back up, James. Sorry, I made a mistake. I mean, okay, it's true. The limit's not 0, but that's not important. I shouldn't be emphasizing that. I don't care what the limit. Well, I mean, I do care what the limit of the partial sums is. But if the limit had been 5, great. The series would converge to 5. If the limit had been 3, the series would converge to 3. But if the limit's infinity, the series, we don't say it converges to infinity, it diverges to infinity. We are adding up terms and the whole sum is getting larger and larger and larger and larger. So this series from n equals 1 to infinity of the natural log of n plus 1 over n diverges. We keep adding up the terms and the whole sum gets larger and larger and larger and larger. So here's a good example of a series whose sequence converges to 0, but the series itself still diverges. So I want to make it extra super clear. The sequence could converge to 0, and the series can really diverge or converge. Both are a possibility. I mean, I should say either are a possibility. You can't do both. It can do one or the other.